Good afternoon. I'm John Bitson, the Menard Family Director of the Sheila and Robert Challey Institute for Global Innovation and Growth. Welcome to the Menard Family Distinguished Speaker Series. I'm really excited about today's topic. Today's topic is a topic very important to all of us, but something very interesting to us in North Dakota, the topic of energy. And I'm really excited about our speaker that we have here today, Dr. Leen Weijers. And Dr. Leen Weijers is somebody who is very knowledgeable about energy and expert in energy. He's also been directly involved in the American Shale Revolution. So today he's going to talk to us about the role that energy plays in human progress and prosperity. And he's going to talk about the economics of the American Shale Revolution and how it's impacted the environment as well. He's going to talk about climate policies and the trade-offs with climate policies. And he's going to talk about the need for clean, affordable, and reliable energy for developing countries. And so I'm really excited about the discussion today. I know that many of you, especially the people that are in my class, have questions that they're going to want to ask at the end. So please get your questions ready throughout the presentation. So Dr. Leen Weijers serves as Vice President of Engineering at Liberty Oilfield Services. He has worked at Liberty since its founding in 2011, originally serving as its business manager. Leen's role at Liberty focuses on two main aspects. One, delivering improved well economics to customers through optimized frac designs. And two, on customer and internal data sharing and reporting to improve business efficiencies. Leen worked at Pinnacle Technologies from 1995 to 2011, where he oversaw development of the industry's most widely used fracture growth simulator, FracPro PT. He was Pinnacle's Rocky Mountain Regional Manager from 2007 to 2011, where he helped rebuild its Rocky Mountain operations. Leen has authored dozens of industry courses and publications. He also played a key role in the calibration of fracture growth models with various fracture diagnostics, such as tilt meter and microseismic fracture mapping technologies. Leen Weijers completed his doctoral research at the Faculty of Mining and Petroleum Engineering at Delft University of Technology in the Netherlands by conducting fracture growth model experiments to investigate the interaction of hydraulic fracture systems with horizontal and deviated wells. Before that, Leen completed a master's degree in geophysics, also from Delft University of Technology. Leen and his wife, Marguerite, have 4 kids. Leen loves to spend his leisure time with family in Colorado's beautiful outdoors on skis, skates, or cycling tires, or on the dance floor. So you didn't bring your tap shoes with you today, so we won't ask you to dance, but I'm really excited. I would like to thank the Menard family and all of our generous donors for making this possible, and I'd like to thank Leen for making the trip from Denver here today in warm, sunny Fargo. So without any further delay, let's all welcome Dr. Leen Weijers.
Thanks, John.
Thank you.
Thank you so much for having me. I've set my timer here at 45 minutes, so we can have plenty of time for discussion afterwards. I really want to thank John and the team here at North Dakota State University for inviting me to speak. And I apologize you have to do with me instead of our new Secretary of Energy, Chris Wright. I'm a poor replacement, but I'll try and do my best to talk about different topics associated with energy. So energy really affects everything that we do, everything. And you can see it, if you look at the world at night, you can see that energy has importance to people to do some of the basic things that we want to do, for instance, with light. This is the border that is visible at night between North Korea and South Korea. And you can see, of course, what the more advanced economy is where people thrive. There are also areas around the world where you see the border during the day. This is an example of that. Energy excess is green. Sounds maybe like a weird statement coming from me. But if you look at this border, the border on the green side of the border, on the right-hand side for you, where you see forests, is the Dominican Republic. And in the Dominican Republic, there's, the economic standard of living is significantly higher than across the border on the same island of Hispaniola, across the border in Haiti, way higher poverty rates. If you look at GDP per capita, about $8 per day per person versus about $30 per day in the Dominican Republic. And of course, with wealth and maybe rule of law that applies in that particular in those two particular countries for that difference, you can see that private or per capita energy use is wildly different between these countries as well. And one of the things that will come back in this presentation that I want you to get used to is GDP per capita per day, but all expressed your entire energy consumption in a day in, say, the amount of gallons of propane you would use. Now, gallons of propane, I think it's a metric that you can imagine, because you probably have a barbecue at home, and in that barbecue sits a 5-gallon tank of propane, typically, for most people who do barbecuing. An average American, all of you here, myself, every American, for all their primary energy use, and that means driving a car, that means cooking your food, heating your home, everything that you do, the manufacturing of products, all our collective kind of energy use combined, and then expressed in gallons of propane, we use about 7 gallons of propane per person every day out of the year, every day. Yeah, so we'll get back to that graph, so I don't have to make as long an explanation of that. But in the Dominican Republic, that's about 1 gallon per person per day. In Haiti, 0.1. Yeah, and of course, that leads to dramatic changes in health, for example. As you can see, life expectancy in Haiti is about 10 years less than it is in the Dominican Republic. And it's because often malnutrition, it's because of healthcare that's available, and often it's also because kids die very early, at a high percentage rate in poorer countries. All right, I want to do a first poll, so we're going to see if our technology is going to work well here. Let's give it a try. And what I want to ask you all first in the audience, first, if you can click on the QR code for those of you who are willing to use technology and give it a go here. So click on the QR code, sorry. And we should hopefully see, my question to all of you is, how much of all our primary energy comes from fossil fuels? And this is, on a world basis. So, right, every individual person in the world, on average, when we use energy, how much of that energy comes from fossil fuels? And we'll give it a little time here before it all levels out. But I like what I see in general, because you're very close to the right answer. And I think more right than maybe most people would be. The right answer there is about 85%. Yeah, on the very highest choice that you have right here. So, and some people are pushing the answer to the right side. Okay, perfect. All right, that's it for that one. Yes, 85%. It's a staggering amount. And actually, in the US, it's about the same as for the rest of the world. The poorer world actually uses kind of higher fossil fuels, especially coal, as a fraction of their use. And we are more kind of in a more advanced economy. Usually, that's pushed more to natural gas and oil today. So a little history here, and how maybe some of the main metric of health is dramatically tied to our use of energy. And for much of human existence on this planet, for hundreds of thousands of years, life expectancy of an average human was about 30 years. And you see that, the line in the middle there, the scale belongs to the right side, about 30 years old. And it was like that for, again, thousands and thousands of years before the Industrial Revolution. And then when the Industrial Revolution started, and with it, our ability to access energy, in the first place, coal, beyond, the excess of energy that comes from wood, dung, and sticks that you use for cooking and for heat. So more advanced energy in coal to power steam engines and to power help for people, if you will, that average life expectancy also increased. And you can see as we go farther here to the 1970s, life expectancy, especially as use of oil exploded, life expectancy went up to 60 or so years. And today, for the world on average, that life expectancy is about 73 years. A little higher in the US, of course, with more access to energy. But you can see that there's a stark relationship between these two, kind of a basic health metric of life expectancy and energy availability. And you can see off of these different colors here in this diagram, again, the 85% of general use of fossil fuels for all our primary energy needs. All right, of course, with that has come emissions of CO2. When we burn oil, coal, natural gas, we release CO2 into the atmosphere. And of course, that number of global CO2 emissions has increased quite rapidly as well. As you can see here, since World War II, we released about 5 gigatons of CO2 on a yearly basis. And that has risen fast through, of course, maybe one metric here, the Yom Kippur War in Israel in 1973 led to increased prices for oil, the Arab oil embargo that affected the US and also my home country, the Netherlands. And of course, made oil quite a bit more expensive to use. But that hasn't really stopped our appetite for more energy as more people use it. Now, of course, the Convention for Climate Change in Rio in 1992 was a start for looking at climate change action. And this is where a path to net zero was first discussed, back in 1992, which would dramatically reduce, of course, our emissions of CO2 into the atmosphere. That didn't quite happen. And of course, with the Paris Agreement in 2016, about 24 years later, this was written into law in many countries. And the path to zero became steeper. And of course, even with COVID, even though we had a temporary reduction in the amount of energy that we consumed in the world and the lower release of CO2 into the atmosphere, still the path to zero is a very, very tough thing to actually implement to implement practically. Another thing I want to express here is again talk about how much energy we all have available as individuals, and this is a cumulative frequency plot, if you will, with on the horizontal axis the amount of people on the planet, about 8 billion people today. And I've ranked all the countries in their individual use of energy, again, expressed in gallons of propane used on a daily basis by every individual. Now, we are here on the top right. US, the bubble size is determined by the population of the particular country. The US is on the far right, where we use 7 gallons of propane per person per day. But of course, way on the left-hand side are many poorer countries, and note the fact that the propane consumption that you see on the right-hand side is actually on a logarithmic scale, right? So some of the very poor countries have consumption levels that are 1/100th of what we use on a daily basis. And with that come different styles of living, if you will. Yeah. So where access to water, transportation, or maybe even the way that we cook doesn't look very familiar to what we are used to in our lives, right? No access to clean water, transportation, just use your feet, and maybe sometimes even barefoot. And then for cooking, often done over an open fire with wood, sticks, or dung. Yeah, dung, that is shit, right? And it's a shitty way to live your life. and actually have that access available to you. That's about 2 billion people on the planet, a little bit more, that cook in that particular way. And it kills about 2.3 or no, about 3 million people every year because of their exposure to PM2.5, particle matter that sticks into your lungs, that's about 2.5 micron in size, that will never get out, and it shortens lives. So the pictures are taken from a book that I love, Hans Rosling's Factfulness. And you can see, of course, that's how the first 2 billion people, the poorest 2 billion, live their lives. A little bit better for the next 2 billion people that have maybe transportation in the form of a bicycle, that have more access to clean water, and that now also maybe use a propane stove. A dramatic difference, not just based on health benefits, that not have these particles move around into a room with you, but also the time saved, especially by women who tend to be the people that are cooking in poorer societies, and dramatic savings in their time to do other things. Then, of course, as we move farther to the right, we get to different levels of energy that we are more or less used to, right? Transportation, a car maybe, access to water through pipeline, and then cooking stoves. And then on the far right, we see a picture of the people who tell us how to use our energy, right? So way different to what we're used to as well. But that's typically the kind of the people who tell us what we can and cannot use in the form of energy, especially the people on the far left. Even in the rich world, we need help with energy. And what we actually put out is quite small. On the left-hand side, a canal in Greece where Emperor Nero said at some point, these 6 miles on the Corinth peninsula, I want to cut a channel. What does Emperor Nero have for energy availability? Slaves. In this case, about 6,000 slaves put to work close to the year zero, and they finished about 1/10 or so of the channel. The channel was finished back in the early 1800s with dynamite, a derivative of natural gas, and that you can of course build without slaves. Which way do you prefer to build your canal? Of course, also in the rich world, energy that we have availability even for dramatic events in sports. If you look, for instance, at the graph on the bottom of that Excel table there, Usain Bolt 100-meter dash. He puts about 2.5 kilowatts of energy for 10 whole seconds and runs a world record, right? That's about what a small air conditioning unit puts out. But this human does it for about 10 seconds. And energy, and that's the equivalent. He used the equivalent of 6/10,000th of a gallon of diesel, right? So of course, the amount of energy that we put out as humans, even for top performances, even if you do a Tour de France or whatever, you bike at an output of 240 watts for 88 hours, that's still only 2 gallons of diesel. Yeah, so it's not the output that we have as humans is minuscule. We're puny and we need help. So energy poverty globally, I've talked a little bit about, the poorest people in our societies who need help. 685 million people lack access to electricity. 2.1 billion lack access to clean cooking fuels. 5 people don't really have washing machines like we use in our society to clean our clothes. They do it manually. But even in the richer world side, there's about 10% of Americans who don't heat or cool their homes to save temperatures. And you will see actually in societies like in Europe, where energy prices are high, more people die during the cold of winter. And the excess deaths are actually related to both kind of the excesses in temperature, if you will. So lower temperatures cause higher death rates, excess death rates, but also high energy prices lead to more death in general. And there's an Economist article that presented data on that recently. So even in rich societies, there's excess mortality associated with energy and temperature. Energy prices, I would say, and lower temperatures. And then 27% of American households experience some form of energy insecurity. All right, poll number 2. I would like to ask you, how much of all our energy, let's move to the next one here, if I can make that work. Sorry. Move to poll number 2. How much of all our primary energy is delivered as electricity? Electricity is just a carrier of energy. It's not a source of energy. It's sourced by wind, solar, natural gas, nuclear power. How much of our primary energy is delivered as electricity? So think about your use of energy, right? Where's your biggest use of energy? And is it electricity? Think about your own life. All right, I'm going to shut this down and move to the next one here. But unfortunately, a big fail of North Dakota on this particular answer. 20%. And in most countries, even less than that. 20% of all our energy use is electricity. And this is often a fault of the media, where people, knowingly or unknowingly, do not discriminate between the two. They say we power, say, for example, 50% of Germany runs on renewables. Their electricity for that day, which is only 20% of their total use. Oil, gas, and coal are the biggest sources of all primary energy in Germany. Right? So you have to make that distinction. And often the media isn't very clear about power. Is that primary power or is it electricity? One is only 20% of the other. And you can see it here in this diagram. This is how different sources of energy are utilized in our lives today. The yellow areas, for hydro, for solar, for wind, nuclear, coal also for a large extent, provide our electricity. And the stunning thing is that these sources do not provide much more than just electricity. This is where oil and gas are extremely versatile, if you will, because oil is, of course, used primarily. That's why, as a source of energy, it's expensive in terms of energy that's available. It's because it's a transportation fuel. It has this massive benefit that you can take it almost anywhere. And then, of course, natural gas is probably the most flexible of all. It provides help for especially heating and cooking, where it's near 100% efficient, right, to create heat from methane molecules. Industrial heat to make things, has a big impact on our ability to make products that we consume. And of course, it's also available as a materials or feedstock for different things that we build or that we make. So, but only 20% electricity. And of course, when you see this graph back, and you've seen it before, hydrocarbons account for about 85% of global energy, prior to 1973. The other 15% was usually that traditional biomass, if you will. But in 50 or so years, with massive growth in energy consumption and also production here in the US, you can still see that hydrocarbons make up about 85% of global energy today. What about climate change? What about health associated with using these products? Obviously, I'm biased, right? Because I'm in oil and gas, you will say, and that is absolutely true. So climate change and air pollution. This is a graph put out by the EPA back in a couple of years ago. You can see on the top here, of course, our gross domestic product has grown by 140% since 1970. And what I want to put your attention to is the graph in red, CO2 emissions per capita. Declined pretty rapidly, about 40% from 1970, with most of the reduction coming, as a result actually of the shale revolution, making natural gas cheap to compete with coal, and displacing coal in electricity generation has resulted in a massive reduction in our per capita, US per capita, CO2 emissions, if you will. That's the red line, kind of in the middle of the graph. On the bottom of the graph, I think, which is way more important, if CO2 is maybe, or there are other sources, or there are other types of materials that you can emit that are way more harmful to people. We already talked about PM2.5, the particle matter. But there's also SOx, the NOxes, and other things that are way more harmful. And these, kind of a combined metric of all of these, is shown in the purple line on the very bottom, down almost 85% since 1970. You can also see that health and hydrocarbons are related to each other in kind of the mix of energy that we have available to us. So this is a diagram. The different colors denote in these societies how much of their energy comes from a specific source. You can see, for example, in Africa, mostly the black source here is the biomass, the sticks, the wood and the dung, if you will. But in places like China, most of their primary energy comes from coal. And you can see the health benefits in yellow. Mortality rate associated with environmental risks are way lower in societies that are heavily energized. CO2 is, of course, also the molecule that builds trees and builds life. Actually, the planet has been greening since the 1970s. And you can see here, this is data from NASA, where actually leaf density has increased in the world. But of course, there's also been global warming associated, partly at least associated with CO2 emissions. And you can see here, this is data from the University of Alabama that keeps track of this on a monthly basis. You can see how average temperatures in the world, and this is kind of the lower troposphere, which is less impacted by what happens near cities and things like that, but that there's been a gradual warming of a little bit over 1 degree, about 0.14 C per decade. And this is where I want to ask you, what you often don't see in these graphs is, well, what is the average world temperature today, say, on land? So how is this, 1.1 degree C change? How is that related to the temperature we all experience on average today? Let's move on, if I can. Sorry. All right, here we go. What is the world's current yearly average land temperature at the surface? 50 Fahrenheit, 59 Fahrenheit, 68 Fahrenheit, 77 Fahrenheit, or 86 Fahrenheit. Now, of course, you're in a pretty far north location, right? But this is the average for all the land in the world. What is the average temperature? Maybe there's some hesitancy, or is it not working, folks? Sorry, maybe I need to do this. Is it not letting you do this? What's that? Okay, or maybe I need to. Is this any better? Sorry about that. It's always the answer in the middle, huh? Tricked you. All right, you're very close though. Surprisingly, the answer is actually 59 degrees, right? And most people, of course, don't realize that, and you never see that data when you look at that increase in temperature. So this is actually data, the graph that I'm showing you here. This is the average world temperature, and you may say, well, why is it rising and falling with the seasons in the northern hemisphere? It's because most of the surface area of the Earth is in the northern hemisphere. It's actually surprisingly lopsided. Most people on the planet live right around 25 degrees north of the equator. That's where the biggest population centers are. So that's why it's rising and falling with the kind of the temperatures in the northern hemisphere. But actually what you see here is that, and this is data from Berkeley Earth, so it's a model actually to calculate what the average surface temperature is based on input from all these different weather stations. But you can see currently it's about 15 C or 59 Fahrenheit. And just for a reference point, the IPCC's report, which they call RCP 4.5, it's about the most common scenario that we're expecting global warming to head to by the year 2100. It's about a 2.5 degrees C warming trend from, of course, where this is. So what you see where we are currently is about 1.5 degrees C warming. And it's expected that that increases by another degree C based on the most common IPCC scenario. You can see here, when we get there, that's 16 degrees C. Where are you as a human most comfortable? It's typically between about 68 and 77 Fahrenheit, right? It may be different for people in Fargo, North Dakota. But think of it, when do you turn up your heater at home? Do you turn up your heat when it's actually 59 degrees F in your house? You probably do, right? So you're probably too cold for comfort. And most of that is true for people on the planet as well. We use way more heating than we use air conditioning, even if you correct for where people live, right? All right, what about sea level rise? Yes, there is sea level rise. Here's an example. Of course, there's satellite data, but there's also gauge data that has been collected, especially in Europe, for long times. This is actually from my home country, collected on various places along the North Sea coast. And you can see a very gradual rise in sea level. And that rise is actually about 16 inches over 160 years. Pretty simple math. 0.1 inches per year. And it's a pretty gradual slope, as you can see. Of course, when there's flooding and there's, depending on storms, the location of the moon and the sun, etc., there's lots of peaks and valleys over that. But the overall sea level rise is extremely predictable. And what have they done in the Netherlands, my home country? Recently, over the last couple of decades, they increased the average height of dikes, of dams, of dunes by about 2 meters. That's that's about 80 inches. And of course, at this current level of sea level rise, that will be good for about 800 years worth of sea level rise. Just something that is done over 2 decades at the cost of about $2 billion to save a $1 trillion economy that lives below sea level today. What about extreme weather? These are trends mostly from Roger Pielke, who keeps track of how many hurricanes landfall, how many cyclones landfall, specific tornadoes over a certain magnitude, droughts, wildfires. You can see the trends here. This data has all the data available for that particular metric. So I'm not cutting off, early times or whatever. This is all the data available. But you see in many of these cases, reducing trends for all of them. And I think the one that matters more is, well, how many people die in these kind of things? And that has been on a downgoing trend rapidly as well, because people use energy to keep themselves safe, right, as protection, as a shelter. So global deaths from severe weather, this is, averaged over decades, has been going down from about 500,000 people on a yearly basis to less than 100,000 people dying from extreme weather events today. So climate change summary. 20th century saw about 9 inches of sea level rise, about 1 degree C of warming, and of course the greatest century of human progress in history, especially with increases in life expectancy and reductions in death by extreme weather. 21st century, the way it looks, with trends in sea level rise, for example, maybe another 12 or maybe 15 inches of sea level rise, with another 1.5 degrees C of warming. Is that an existential threat? I want to talk a little bit about power sources and the things that we are led to believe they are or are not. And some of the concepts that we hear often about different power sources. Is a power source clean? There is no power source that's clean. Of course, you need to know what the metric is. But for example, we may all think sitting around a campfire and cooking is a great thing to do. But if you do it every day and you inhale the particle matter, that gets stuck into your lungs, it's not a great thing, of course, to be around for life. So is that clean? No. And I think often we use, for example, CO2 as a metric of what is clean, and a reduction in CO2 is clean. But if it comes at the cost of something else that costs human life, can we call that clean? I don't think so. Another thing, what is green? Often EVs are called green. On the right-hand top, I have a graph, the carbon footprint of EVs versus their internal combustion engine, kind of similar size car. Volvo and Volkswagen did great studies on this. And what I'm showing you here, for instance, focus on the red, blue, and green solid lines on the right-hand side. So these are internal combustion engines, easier to make with respect to a carbon footprint. They have their lowest carbon footprint at kilometer zero. At kilometer zero, an EV, because of the more complicated engine, the extra metals we need, etc., has a higher footprint when you haven't driven the car. But it uses less CO2 as you drive it. And often, you earn your CO2 back, if you will, after you've driven 80,000 or so miles. And then, of course, if you drive it to maybe the life expectancy of that car, the EV is maybe only 10, 20% greener, in the emissions of CO2 over its life cycle. Is that worth it? The 20% greener, you could have bought a smaller car, or you could have done something else to dramatically reduce your CO2 footprint. The EV is not the way to go, and doesn't really earn its subsidies from just a very small reduction, as people trade kind of gasoline use for use of diesel and coal to build it in China. On the bottom graph, using extra land. So renewable energy sources, solar and wind, are extremely needy of land, right? They use a lot of land. If you look at the scale here, power density in watts per meter, corn ethanol is probably needs about the most amount of land when it comes to producing a watt of energy. You can see here about 0.1 watt. Hydro is maybe at about 1 watt or so per square meter. You can see solar maybe at 10, wind at about 5, but coal is at about 500, and nuclear is close to 10,000 watts per square meter. So way more efficient use of land, if you will. And of course, then humanity can use that land for something else. What is reliable? I grew up in the north of Holland, next or very close to the German border. If you look across the small sea over there, Germany is out there somewhere. This is on a December day. The sun isn't shining. If you look at German power generation from solar, they have about 68 gigawatts of capacity in solar. 68 gigawatt would power that nation any day, any time, if it's nuclear. Yeah, so 68 gigawatts is slightly below average German power consumption. What does solar do though? In the summertime, when the sun is out, but Germany is pretty far north, farther north than Fargo. It's about as far north as Edmonton. Yeah, so if you use solar power there in the summer, it is about 17% natural capacity factor. In the winter though, it's only a tenth of that. The sun maybe works only 2 hours a week. Would you hire that worker for 2 hours a week? Is it cheap? What is cheap? Intermittent solar, for example, here, looking at the energy, residential energy cost in California and in Florida, you can see usually, of course, what we hear about often is that renewables their cost is lower and lower and lower. And usually the metric used there is LCOE, or it's the levelized cost of energy. Yeah. On that metric, these sources are indeed getting cheaper. But what an LCOE metric does not include is intermittency. It's like, an Uber is pretty cheap. If you get your Uber, but you have no idea when he comes or when he or she comes and where he or she will go, would you take that Uber? And that's why I think in general, what you need to do when comparing energy cost is to use the full system. LFSCOE, if you will, that's the levelized cost of energy, but for a full system. And generally what you see when you have more intermittent sources in your system, you have to overbuild, you have to rely more on battery power. That's expensive typically. And generally your electricity becomes more expensive when you incorporate these intermittent sources. What is secure? China chooses coal to securely manufacture all our stuff, everything that we need. It's kind of surprising how China has grown its energy use. They're at about 160 exajoules, if you will. We use about 100 exajoules in the US. So China is definitely producing and consuming more energy than we are. But you see about 50% of the growth in the last 5 years is from coal, as you can see by the bar diagram. Yes, there's growth also in oil, natural gas, nuclear, wind and solar, but coal rises above it all. We've done it different in this country. Over the last decade, these are all the power sources, and I'm not using the exajoules, but quads, and this is quadrillion BTUs, which are almost a one-to-one comparison with the exajoules. Today, we're producing about 100 quadrillion BTUs in this country. And you can see over the last decade and a half, that production of quads or exajoules or energy has grown quite dramatically. Now, on a compounded growth basis, our yearly energy production has increased by about 2.8%. Renewables are keeping up with that rate at 2.9%. It's the sliver on top of all our energy production. And then nuclear, since we're not building nuclear power plants in this country today, I should rephrase that, very little. But nuclear, since its power has not really increased, not grown very much. Of course, when everything else is growing, it gets behind as a fraction of its energy production. Number 1, 2, and 3 on the Olympic podium for growth, though, of power sources in the US, natural gas, NGLs, and oil. And this is where the Shale Revolution comes in. But 72% of all our energy produced is oil, gas, or NGLs. About 80% of that 72% comes to you through fracking. So all your primary energy consumption as a person, about 60% is probably touched by what happens on a frac location in North Dakota or in South Texas. 84% of that is fossil fuels. Just one maybe little peek into the shale revolution. I want to show you how frackers and drillers have become more efficient in bringing oil and gas cheaper to consumers. It's a pretty full graph, and I apologize, but let's start on the top left. And this is a ratio that I want to express. On the top left is a graph that is the cost for an average well that we're drilling in the shale revolution in the US. To drill and frack a well 10 years ago cost maybe about $10 million. Today, a well in North Dakota maybe cost about half of that. As you can see, all these colored lines, those are different basins that are rich in oil in the US. So significant reductions in well cost. But that's not the most important part. The most important part is that we are better at extracting oil from each of these wells. That's the graph on the the bottom left. That's the first production out of the first year of each of these wells, gone up from 60,000 barrels per well location, to 160,000 barrels in just the first year of production. It's pretty typical for a North Dakota well. A well will eventually produce between maybe 500,000 and 1 million barrels, but in its first year, it will do something like that. Combining these two gives me the graph on the right. That's dollars per barrel. How much does it cost to bring a barrel of oil to the surface in the US? That number has come down dramatically as well, as you can see by the colored line in each of these basins. If I plot that on a kind of production, barrels of oil produced per, or the cost to bring a barrel of oil to the surface, is down almost 70% since the start of the shale revolution. And if you compare that to the price of West Texas Intermediate, you can see that break-even cost, using this very simplistic metric, have gone down from almost 2 years to produce a well to break even, to get your money back for what you did drilling and completing it, to today less than a year. There's lots of potential in the world. There's lots of countries that have massive gas and oil reserves. The US has proved reserves, a good metric for kind of what we can produce today with today's technology, but 70 billion barrels. Today we produce probably about 4 or 5 billion barrels on a yearly basis. So you could say, you know, we could last 10 years with the proved reserves in the US. But the truth of the matter is that this proved reserve number moves up with time as we know more, as we know better how to extract things. And that proved reserve stands against, say, sorry about that, it's my cue. That proved reserve stands against a 4 trillion barrels of oil in typical US liquid-rich reservoirs. Of course, even if we can get 10% of that out, that's 400 billion barrels, right? That's way higher than the current proved reserves, a very cautious metric of how much oil we can produce. So just for reference, have you ever been to Lake Erie? Think that full of oil. That's currently what is present in 6 US shale reservoirs. The volume of Lake Erie, and it's a little bit larger than that, it's actually about 150 cubic miles, right, is what we have in US shale reserve. The trick is, of course, to get it all out efficiently, but that's where innovation and technology comes in. Of course, in the rest of the world, there's lots of areas with lots of oil and gas as well, but you have to look at the economic and freedom index, if you will, to see, you know, typically if these countries are ripe to actually host a shale revolution of their own. And then finally, a little bit on nuclear power. Of course, we just built our first nuclear reactor in Georgia in a few decades, but it's expensive. And part of the reason why building nuclear power plants in the US on, say, a per megawatt power output metric is about 4 times as expensive as it is in India, for example, or in China. Part of that is that we've regulated it out of business, and it's very hard to build a power plant and everything associated with that. All right, so quick energy source summary. Many people have yet to finish the energy transition from wood to coal. Past energy transitions were driven by people. Renewable energy is top-down, fed by government. The shale revolution and natural gas replacing coal has significantly reduced US per capita CO2 emissions. And of course, where I hope it goes in the future, that there's more energy for everybody, and that there's an eventual transition likely to nuclear, continuing a trend toward denser, cleaner, cheaper, reliable, and secure energy. Just a few more things here. I'm going a little bit over my time, 2-3 minutes, John. Okay. So one other book that I like a lot is 12 Best Things, or Best Things First, I'm sorry, by Bjorn Lomborg, a Danish economist. And he looks at things, what is, say, the benefit to cost ratio by attacking certain things that are in the Sustainable Development Goals from the United Nations. What is the lowest hanging fruit that we should all pursue? Maybe if we had a pot of money, where would I put that pot of money to advance humanity in the best possible way? So he looks at the benefits to cost ratios of various things in his book, which is fantastic. Best Things First. He wrote it just 3 years ago, I think. And he comes up with several things that will give the UN a lot of bang for their buck. And one of the things in there is also clean cooking fuels, right? I talked about the 3 million people that die prematurely because of exposure to these small particles. That's one thing we can easily eradicate. It's actually Foundation and Bettering Human Life Foundation that we sponsor heavily at Liberty. To attack that particular problem. Instead of indoor cooking with wood, sticks, and dung, we help innovators, business people in Africa to bring propane to people and replace their use of these materials that harm people. And then one other thing that I want to pay attention to is a book here by Magatte Wade. She's from Senegal and a huge business proponent to advance Africa. And in her book, The Heart of the Cheetah, she defines poverty and what people need to do to travel the road to prosperity. She asks a few basic questions. What defines poverty? No money. Where does money come from in your personal life? A job. Where do jobs come from? For-profit businesses who want to keep their head above water by being profitable. And where do these businesses thrive? In free societies. That's, I hope, a lesson for the world in providing more energy to people. And that's how, together with technology, we can bring energy to the people who mostly need it in the world. So poverty is the topic that requires our attention. There is no climate crisis. Does the climate change? Yes. Is global warming happening? Yes. Is there more CO2 in the atmosphere? Yes. Is it a crisis? No. There's no energy transition. Currently, there's just energy addition. And poverty reduction requires cheap, abundant, clean, secure, and reliable energy. Solar and wind today supply about 3% of the total global energy after trillions of investments. Or, taxpayer money. The American Shale Revolution has lowered the cost of energy to world consumers, and finally, abundant natural gas can provide a transition to denser, low-carbon, nuclear energy. And I think states who recognize that will have an advantage on the world stage. I thank you for your attention, and I'm open to any questions you may have.
Oh, thanks. Thanks, Leen. That was a super informative, great presentation. I learned a lot, and I know everybody here learned a lot as well. So I think some of the things, I mean, you did, it's great that I'm glad all the people showed up here, but I think there's a lot of misinformation about, some of the things that you presented. I mean, people aren't aware of these things. I mean, so for example, the idea that I think people think that most of the energy that we consume is in the form of electricity, for example. If you show people that deaths from natural disasters have gone down over time, if people get so emotional they don't even believe you. Or if you show them that there's not a pattern of increasing natural disasters over time. And so even I was looking up yesterday the UN climate action, and so they showed that 107 different countries had pledged to have net zero greenhouse gas emissions by 2050. But then they said that if the countries that had signed on to this did what they said they were going to do, it met their commitments, that by the year 2030, they would reduce global greenhouse gas emissions by 2.6%. And they said in order to reach the goal of net zero by 2050, they'd have to reduce it by 43%. So I think the UN doesn't even believe that this is possible, but by continuing to say, net zero 2050, they make it sound like it's just easy. We can just go ahead and, switch all of our electricity to, wind energy or something like that. And that's all of our energy. So how do we spread the word other than, getting more people to come and see you speak? How can we, let people know about the facts so that we can, because I think everybody, and you might say, well, people don't have to be informed on everything, but everyone has an opinion on climate change, and you can't have an opinion if you don't understand these facts, or a reasoned opinion, I think. So Any thoughts on that at all?
No, I think, we have to have an open discussion about all of that. And some of that may be radical to some. But yeah, I would always say, do your own research if you're interested in this. If you don't believe me, that's fine. Look for yourself. But of course, there's a lot of, unfortunately, misinformation or people pushing a certain thing, and I may be doing a little bit of the same thing. I can't say that I'm not maybe guilty of something like that, because I'm of course biased myself. But I think a lot of this, if you dive deeper in, for instance, the IPCC reports. Unfortunately, what happens with the IPCC reports, a lot of scientists work on it, they come to certain conclusions, and then there's actually a group of people that are not the scientists that write the summary, and the summary is written for policymakers. And it's often written by policymakers as well. And it doesn't really even closely resemble what the scientists have come up with. And this is the information for policymakers, is what we hear and what our policymakers distribute to all of you. And they don't know any better, right? Because it was actually, the summary is different from what the scientists have said. And what I think is, unfortunately, and there's definitely some scientists that are speaking up about that, but that there's no more kind of word from the scientists themselves. Maybe they don't speak our language, but that if you dive into the thousands and thousands of pages of the IPCC reports that they put out every 5 or so years, you can find a lot of these things right there. And it's unfortunately that there's this. I think the only thing we can do is talk about it, have a frank discussion, point out to people that, maybe this is not accurate, or I have a different opinion about this because of these and these reasons. And that's all we can do.
Yeah, thanks. And I think I left out probably the most important form of misinformation. I think that people don't understand the human cost of trying to push that agenda. I think people are surprised when they hear that more people die of cold weather than hot weather, and
Yes.
and the fact that you're preventing development and actually costing human lives if you push that agenda too far.
Yeah.
So another thing I'm interested in, I toured an oil rig out in Western North Dakota a couple of years ago. One of the things I became aware of, which is probably old news to other people, but I didn't know about it at the time. I knew about carbon capture, but I didn't know about the idea that you could actually capture the carbon and it would enhance the recovery of oil. So I'm wondering what do you think about that technology? Do you think that, are we going to be able to open a lot of wells that we thought were not viable wells anymore? And also, do you think it has merit for dealing with climate concerns that people have?
Yeah, good question, John. And I'll maybe to start with kind of the technological question, when I talk about the shale revolution, and often when people talk about how much a well can produce, typically, over the well's life, and if we would put a lot of straws in the reservoir, if you will, if cost was no issue, right, we could maybe, from the primary mechanism of production, just the pressure in the reservoir that has pressurized that kerogen and changed it into oil and gas. The reservoir at 10,000 feet has a higher pressure. And just when you stick a straw in it in the form of a well, there's a natural tendency for that oil and gas to flow to the low pressure area, which is at the surface where we consume it and things like that. But when we do that, typically for an oil well, we only produce 10% of what sits within the pore space of the rock in what we call the reservoir. So how do we get access to the next 90%? And that's often, you have to do quite a bit more work for it. You maybe can pump into it CO2 or propane or natural gas if there's excess of it. In some reservoirs, you can actually put water, right? You can have what is called a water flood. So pushing water from one side, pushing oil out of the way toward other wells with a producer or with an injector and a producer well. In shale reservoirs, it doesn't work as simple as that because the rock is way too tight to push water or anything through it. So you have to resort to other methods. And we're still learning what kind of methods we should use. And injecting CO2 in some wells and then producing more hydrocarbons in other wells is maybe one way you could do that. There are other ways that we're looking at as well. So that's maybe, I'll keep it vague like that if you don't mind. Then the cost side of it, one of the things we often look at is, if reducing CO2 is important to you, and of course it is to many people and to many policy people in the world, I don't think I always agree with them that CO2 is harmful and that it needs to be reduced. But if your point is that you want to reduce CO2, right, then you should look at economy, the economy of that as well, right? How is it the cheapest to get a molecule of CO2 out of the air? And unfortunately, direct air capture is quite an expensive way to do so. There are industries that are working on directly, say, for instance, powering power plants where you burn, say, coal or whatever with a flow with an airstream, or not with an airstream, but directly with oxygen instead of the nitrogen that causes all these additional reactions that causes harmful other emitted materials. And there are other methods as well that we as a society are working on to reduce the amount of CO2, even if you're using fossil fuels. And of course, you can also reduce them if you're using maybe some of these other technologies. Renewables, of course, typically have a lower CO2 footprint, although they have a significant CO2 footprint by themselves from building the materials. But you should always look, I think, when that is your goal, to get CO2 out of the atmosphere, what is the cheapest way to do that? And direct air capture is usually not the cheapest way to do so.
Okay, great. Yeah. Thanks. So I'm going to ask people to come up and start asking questions. I'd like to leave it to them, but while people are gathering, and I know all my students are going to ask questions of you, but while people are gathering, the first, I just want to have one other question on technology. And so to me, it's interesting. You just talk a little bit about how the technology has changed recently in terms of, producing oil, in terms of like maybe fracking for longer distances horizontally and other types of technology that have changed, and something maybe that's promising for the future. Yeah, when you look at the shale revolution, and sorry, I'm gonna maybe let you wait 2 or 3 minutes if we're answering this question. I'm sorry. In the shale revolution, there's two critical things, right? Fracking and drilling horizontally, and fracking in multiple stages. So if my arm denotes, say, a horizontal well that's driven down in the Bakken at 10,000 feet, we break this rock up. We break the section, the 10,000 foot lateral, in maybe 50 frac stages individually. We frac the rock here, set a plug, frac the rock here, and we do so, rinse and repeat, if you will, 50 times over a period of a week, and frac a well sequentially in multiple stages.
So what is really key to making a well produced, to see that production go up from 60,000 to 160,000 barrels in its first year, is the extent of that network, the radiator that we create with all these fractures, and the density of these fractures in between that space. So increasing the size of the fracture system, the radiator, and the density of surface area kind of within that radiator. And there's different things that we've done as an industry to improve all of that. Bigger frac jobs, higher intensity rates, targeting, changing perforation strategies, things like that that we've done to make wells produce from that radiator downhole.
Okay.
That make sense?
Yeah, thanks.
Yeah,
Yeah,
thanks. Sorry.
So you mentioned biofuels and ethanol being very land intensive. Do you think, though, given how important energy is to having a developing, prosperous economy, it's a good idea for public policy makers to incentivize ethanol and other biofuel production?
Yeah, I'm not going to be very popular here, but probably not. I would advocate no subsidies for any energy whatsoever. I think the most efficient thing to do is the marketplace to figure it out. And we as oil and gas, if you will, that I represent here maybe, of course, we get, subsidies to a degree as well, right? So guilty as charged. Typically, the subsidies that we receive on a per energy produced basis are very small in comparison to other things. But so maybe let me start there. I don't like subsidies whatsoever in how they distort the marketplace. But if there are people, of course, who wanna use it, if there's an incentive for more of that ethanol to be used in our consumption, sure, but let it compete in the marketplace.
Thank you.
So we read the book from Liberty in class, and I kind of had a question about, they gave an example in the book of Germany reducing their energy use, and it ended up reducing the standard of living. People couldn't afford to heat their homes, and they ended up having to import energy such as coal into the country just to make sure that their people could heat their homes and stuff like that. So do you think, and they ended up not having that much of an impact on reducing carbon emissions at all?
Yep. Mm-hmm.
So do you think that we should not focus on reducing carbon emissions altogether because it doesn't really work? Or what are your thoughts on that?
No, I wouldn't go that far. I think, certainly, and I think unfortunately in the media is often about climate change, one problem, one solution. The one problem in the world to top them all is climate change. And the only way to fight climate change is to reduce CO2. These are two fallacies, I think, right? So is there a truth to some of it? Yes. Of course, climate change is happening. CO2 as a molecule, when the sun shines on it, retains more heat, and that causes some global warming. There are other molecules, water, steam, for example, does that even in a way worse way. Never mind that, but CO2 does have that particular feature associated with it. But I think what we are often presented with is again the single problem, single solution mindset. The single solution doesn't work either. I think it's way from an economics perspective. For instance, what Holland did with building dikes and dams and things like that. Yeah, they're a country that is, about 1/3 of it is below sea level. The most economic active, where most people live, part is below sea level. And to protect that $1 trillion economy with 10 million people living in it, they just, secured their future by, just increasing the height of dikes. I don't have to rely on anybody if you want to use more CO2, if there's more global warming coming. I have taken care of myself. For a 0.2% of the GDP of this country, I can protect myself, right? So it's way cheaper to adapt something that humanity is great at. So I'm sorry to finally get to your German side of things. So yeah, unfortunately, I think Germany's decision to not go with nuclear, right, and to go full solar and wind, has led to higher kind of larger unreliability of their electricity grid. And the unfortunate thing, as you mentioned, one of their goals is to lower CO2, is in order to be able to provide backup power in the absence of nuclear, which doesn't emit much CO2, right? They've actually resorted to regular coal, and especially brown coal, which comes from Germany itself. It's in their own country, but especially high in CO2 emissions as a replacement fuel for nuclear. So it's a very strange dynamic, I think, where their goals are not met at all. And you've made your electricity, their electricity is more expensive than anywhere else in the world, in Europe for sure. And I think part of it is tied to that unreliability of renewables and backing it up with more systems, if you will, and especially ones backing out of nuclear for their backup power. Sorry, that was a long answer. Thank you for the question.
Great speech, by the way. I was just wondering if you had any advice for college kids on if there's anything we can do on a day-to-day basis to help out those who are struggling with energy poverty.
I think you've seen that in my presentation. What I hope to achieve with some of these presentations is awareness that if there's some people. Chris Wright, our past CEO and current energy secretary, he uses a phrase, and it's probably from somebody else. Say that the lucky 1 billion, we are all part of it, right? We have very rich energy lives, very rich lives. We have a lot of energy available to us. Leonardo DiCaprio can spend 3 times what an average human being consumes in a year in a 45-second rocket ride, right? So our energy consumption sees no end to it, if you will, right? And good for him that I think he can do that with the money that he has. But I think there's often not an awareness that we need to bring energy, make it cheaper, reliable, clean, more secure for all these 7 billion people that are not as lucky as we are. And I think that's why I'm proud to be in our business, that we provide very high-end, efficient energy to many, many more people who've access to oil and gas that is in this country cheaper than it's been for a long, long time. So I think if you're if you're going into a specific area where you can be part of kind of pushing that energy agenda, if you will, I think that can be a win for everybody, right? And I appreciate your question.
Thank you.
Thanks.
I have a question. Hi, so I want to know your definition of what is a climate crisis, and at what period or what time should we start getting worried that we are in a climate crisis? Number one. The second question, I see there's a blurry line between what is cheap and what is sustainable. So how do we ensure, example, we know that our a cooking ware, the PFAS, which is being used for, what do they call this thing? Cooking ware to non-stick pans, despite the fact that it is cheap, but it's not sustainable because it contains poisonous compounds that affect human body. And over time, we could see that most people that ingest this thing have increased rates of cancer and all. And I was curious to know that, despite the fact that it's cheap, but it's cheap for who? This generation, next generation, first world country, second world country, third world country. Who is the biggest? Who are the people gaining more from this cheapness of this energy? Thank you.
Great question. Thank you. Maybe to start with the first one, I think what is a climate crisis? I think. Of course, there's many people who have proclaimed that there's a climate crisis, right? I don't know exactly what they mean with it, but what they do or what they want from a policy perspective is that we throw massive subsidies into resources that are not as efficient and maybe secure and reliable as other methods of providing energy. And I think, unfortunately, climate change should definitely be in your awareness, right? And something that is happening today. And maybe it happens against what is happening naturally anyway, since we came out of the little ice age in the 1700s, and our rapid advancement in energy production is kind of in tandem with kind of the natural cycle out of that little ice age. So I think you have to be. Of course, when you proclaim that there's a crisis that, and throw everything into renewable resources, assume that there's only one problem in the world that only has one solution, climate change, mitigation of CO2, I think you're simplifying things. And I think not only are you simplifying things, you're also, anybody who kind of gets away from that problem and the single problem and the single solution, I think is also not justifying how complicated the issue is as well, right? There's many aspects to climate change that you're ignoring with your single problem, single solution. And I think the sad thing that I hope to emphasize in my talk is that when you're emphasizing that single problem, is that when you're asking people in poor countries if climate change is important to them, they have way other things to worry about than climate change. Does that mean it's irrelevant? No. But does it mean that we are taking attention away from something that 7 billion people on this planet find way more important than the rich 1 billion people that we represent? I think we should listen to that. So that's maybe my first, I think, answer to your question, if that's it. So climate crisis, if you will. There's other crises that I think require more of our attention, and that are probably also way easier to solve. Then your second question, I apologize, I'm blanking.
I think it was about the non-stick pans she was talking about.
Oh, I see.
Yeah, cheap for who, I guess you said. Oh, okay.
Yeah. Yeah. Yes. Yeah. I think, everything in life involves trade-offs is something that, is a favorite saying of my previous boss, Chris Wright. There's pros and cons to everything. Oil and gas are not perfect, right? They are not perfect, but I think typically what we as humans do is we weigh benefits against cost, right? So what can we, does that mean that, nobody ever will die from the consumption, their use of a specific energy? No. But we as a society, I think, make trade-offs, right? And it's hard to do that economically when lives are involved. That is a tough thing to do. But I mean, in reality, that's what we're doing in our everyday lives, all of us anyway. So you have to weigh the pros and cons of these things. And often when people talk about fossil fuels, for example, they talk about kind of the cost in lives. So for example, you often hear the number thrown out, 7 trillion kind of hidden cost in using fossil fuels on a yearly basis for the world, right? And if you dive into the details, an IMF report, the $7 trillion comes from early deaths associated with mostly outdoor air pollution near coal plants, right? So if you can actually do the math, and the IMF does that, there's actually a value for a human life on a yearly basis. It's about $5,000 for a person living on the earth on a yearly basis. They use a metric for kind of a human value, if you will, the value of a human life on a yearly basis. And that's how the IMF and the World Bank evaluate trade-offs. And outdoor air pollution from coal plants is not as prevalent as kind of the indoor air pollution problems that I mentioned before that kills about 3 million people every year. They handily, what the IMF and the World Bank do is say when a poor society switches over from cooking fuels like wood and dung to coal, electricity, propane, and things like that, what they conveniently forget is that these biofuels kill way more people than kind of central coal plants. They calculate there's so many more deaths, early deaths because of pollution from coal, but they forgot that these societies came from, people that died from indoor air pollution. So what is often happening when you're seeing kind of the benefit or the cost of fossil fuels is an evaluation that only looks at the cost. They don't look at the benefits to society. I think if you give people in developing country the choice, would you rather do indoor cooking, that maybe doesn't produce as much CO2, but that creates these PM2.5 particles that gets lodged into your lung? Would you rather have that or a coal plant that gives you electricity to cook with? What do you think they will choose? They do their own benefits to cost analysis, right? And they will probably choose the latter. Does that answer your question? Thank you.
Is there one more student with a question there?
There's two over there.
Oh, I saw.
They've been waiting longer.
Yeah.
Well, thank you very much. I have a question about the radiative capacity of CO2. We've gone from 220 parts per million to 440. Some of that caused by humans, and that has had some radiative effect. But it seems to me that after 440, if we double or triple, there would be very little radiative effect. I think McKittrick and Happer published papers to that effect, which have been ignored. Yes. But we still see these extrapolations of, we're going to keep on, temperatures are going to keep rising. Even if it's small, it adds up over time. But it seems that there is a limit to what CO2 could contribute. Is that true?
Yeah, I think you're certainly there's definitely some science behind that. I think maybe to rephrase, pre-industrial CO2 levels were about 280 parts per million in the atmosphere, right? So 280 parts per million. Currently, we're at 420 and about a 52% raise in CO2 levels due to all the CO2 that we've emitted in over the last 150 or so years. Typically, when people talk about, say, the RCP 4.5 or RCP 8.5, the plans or the scenarios from the IPCC, if you will, those are for a doubling of CO2, and that's typically, say, from 280 to 560, right? So we're halfway to a doubling of CO2. So when people talk about that radiative forcing of 4.5 watts per square meter, that's the RCP 4.5. That comes with a temperature increase that's expected about 2.5 C or so. So that should happen if we're on that path. When we hit 560 ppm in the atmosphere, probably somewhere near 2100, that temperature the Earth temperature will have increased about 2.5 C since pre-industrial times. Then a doubling, if then things can double again for kind of a similar temperature sensitivity. So there is some kind of exponential function going on there, right? So doubling there, and then another doubling of CO2 would create the same 2.5 degrees temperature increase. Or am I misstating that?
I don't think their proposition. I think they were talking about going for 40 now.
Okay. 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 I do not know that particular paper, but is this McKittrick? Okay. Yeah. Okay. Thank you. Sorry.
So this is a bit of a two-parter, but on your point 7 of your conclusion, you said where shale oil and natural gas will lead the way to nuclear power use. Is there any like broad steps, or what do you see the broad steps are to facilitate this transition? And the second part would be, is there any legislation or regulation changes that should be made?
So point 7, I think it's still on the, I think it's, oh, my projection is gone. So the shale, so can you rephrase it again? The first question was about the natural gas or the shale revolution expanding to elsewhere, or?
Yeah, the expansion of the Shale Revolution would lead to nuclear power, like kind of taking
Yeah.
over. What broad steps do you see need to be taken for that to occur? And then is there any legislation or regulation changes that need to be made for this to occur as well?
I think definitely kind of a world without subsidies, I think would go a long way to kind of make the best energy source for whatever you as consumers choose it to be, right? Instead of the government making choices for us. I think that's a very important part of, I think, letting the marketplace decide what is best. So I think that's in different countries, that is also, you need to provide an environment that's business friendly, where, property rights are respected. I think the reason that the shale revolution happened in the US, I think one of the primary reasons for it is property rights, and the fact that our citizens mostly own their mineral rights miles below their feet, right? And so there's always an incentive. I want to develop my, my particular area or what I own, and I want somebody, to help me with their expertise to do so. Now, you don't typically have that in many other countries in the world. The governments own the property, own the mineral rights below, say, 2 meters or so below the surface. And so there's less of an incentive from individuals to develop it. And that's, I think, why the shale revolution happened here. So, and of course, one of the things to realize when there's shale development near you, I live in Denver, Colorado. It happens, not too far from the city of Denver. Development can be a nuisance, right? There is definitely impact on where you live of what the industry is doing. There's more truck traffic, things like that. So I think in general, when you're developing things in other countries, where you don't have the property rights, and where local people cannot benefit from its development, things go wrong often, because the incentive of the local population is not aligned with the incentive to produce that energy or have cheap, reliable energy for everybody, maybe in that country. I think you need to have the kind of the local population as a partner into how that development should take place, and also have them as a partial beneficiary of that development. I think where you don't do that, I think it goes wrong. And typically we have that built in through mineral right ownership in the US. In other countries, it's not as direct a relationship. I think that's probably the most important thing. That's, and to speak with Magatte Wade, for example, you need a kind of a country with rule of law that respects freedom for people to build businesses, so that you can actually have your population thrive and make money. So that is something that you need to build infrastructure for, kind of the efficiencies we have in this country for instance, the energy that we put out. Just as an interesting stat, I think, when you look at how many people work in oil and gas to extract oil and gas and provide it as 60% of the energy through fracking for all US, for all 335 million people, right? So the wind and solar industry has about the same amount of workers on the ground to install solar panels and things like that, but they produce 70 times less energy to oil and gas workers. Right? So who would you rather have, as a contractor? One person who can do it all, or 17? Right? So I think efficiency, to get to those kind of efficiencies, you need to you need to have the infrastructure and freedom for people to thrive and build that for. So, but I think it starts with kind of the mineral rights and kind of the freedom of, for people to do whatever they feel they want to do.
So this is perfect timing. We were going to do a demonstration almost of the importance of fossil fuel to people because I forgot to get gas last night on my way home. So we're riding on fumes on the way here, but we made it. So anyway, so thanks again. This is really a great discussion. I know we could have had more questions. And so there's time that you can ask questions if you want afterwards of Leen. And so thanks again, Leen, for being here. Appreciate it.